Okay, welcome back to the fourth part in this five-part series where I derive the critical t-value for students' t-distribution. In this fourth part, I'm actually going to give an analytical formula for the critical t-value with v degrees of freedom. And I'm going to start by taking a look at this schematic that we were looking at earlier. If we remember, the green is the area under the curve between the critical t-value, the negative critical t-value, and the positive critical t-value. And so, if we remember, the confidence interval is equal to 1/2 that area minus eta, where eta is one tail, is calculated using, is for one tail of the distribution. Bearing that formula in mind and that schematic in mind, what I want to do now is extend this formula that we drove last time and try and actually isolate that critical t-value, that t-star value. So if I write the following, which is that 1/2 that area term minus eta is equal to the critical t-value, we can immediately see that that area is really equal to 1 minus 2 times eta, where 2 times eta is really equal to beta, where beta is simply 1 minus the confidence interval for a two-tailed distribution. So bearing that in mind, we can write this formula now as 1 minus 2 eta is equal to 1 minus the regularized incomplete beta function, whose arguments are v over 2 and 1 over 2. And if we remember, we had a transformation formula which said I sub z of AB is equal to 1 minus I sub 1 minus z b a. And that was from earlier, where we were working on deriving that value. I'm trying to find it real quick. I can't remember quite where I put it. That was here, right? This term at the bottom here. So if we write that out in full and rearrange a few terms, we're going to get that 1 minus 2 eta is equal to 1 minus 1 minus I, 1 minus z b a, where z is equal to this term, which I'm actually going to call this x sub t for now, and a is equal to v over 2, b is equal to 1/2, which allows us to then write 1 minus 2 eta as being equal to I sub x of t of 1/2 v of, it's actually 1 minus x of t of 1/2 v over 2. And if we remember what the actual definition of this thing is, it's 1 over beta of v over 2, 1 over 2, times the integral from 0 to x sub t of some variable. We'll call it, actually let's call it u for now. U to the negative 1/2 1 minus u v over 2 minus 1 du. And, oh, again, I made a little mistake. It's actually 1 minus that. Put this over here so it's out of the way. Now, we can rewrite this even further as beta of 1 over 2 v squared times 1 minus 2 eta is equal to 0 1 minus x of t u to negative 1/2 minus u v squared minus 1 du. Now, this is an important part, because what we want is we want to solve for x sub t, because that's going to enable us to pull out that critical t value. And it turns out this is actually possible, but it wasn't clear how to do it. But there's a paper by a fellow named Diego Dominici, called Nested Derivatives, a simple method for computing series expansions of inverse functions in 2003, so some fairly recent mathematics, which enables us to actually solve for x of t in the above integral. In order to do that, we need to rearrange the integral sum and make some substitutions. So first of all, let's look at this integral, and essentially what we have is we have the following. One minus u of, I'm going to write t, 1 minus t of v over 2 minus 1 square root of t dt. I'm going to make a u substitution, so I'm going to call u square root of t, which means du dt is 1 over 2 times the square root of t, which implies that 2 du is equal to 1 over square root of t dt. I'm also going to call a v over 2 minus 1. So here are some of the substitutions I'm going to make in order to solve this problem. And that's going to transform our integral into something to which we can apply this method of Diego Dominici. going to enable us to actually get an analytical definition for our x of t, which we'll rearrange. So rewriting the integral, we can write that u of 1 minus x of t and u of 0, whose integrand is this guy, we're just going to say it's equal to some constant. Again, the constant we show to be that beta term times 1 minus 2 times eta. So now we're going to actually introduce this theorem, and it's by Dominici, 2003. It goes like this. It says, let h of x, some function of x, be an integral from a to x of 1 over f of t dt, supposing f of a is not equal to either 0 or plus or minus infinity, where capital H of x is the inverse function of x, then we have that h of z is equal to a plus f of a times the sum from n equals 1 to infinity of this operator, capital D, raised to the n minus first operator on f, evaluated at a, multiplied by z to the n all over n factorial, where this operator evaluated at 0 for any function is equal to 1, and where values of this function, values of this operator are equal to the derivative of the function multiplied by that operator calculated at previous values of f with respect to t, all evaluated at a. So this is a key theorem, and it's perfectly suited to solving this problem, and it actually enables us to make some progress on getting nice, well-behaved values for that upper limit. So now we can apply the formula. And this is not so simple, but basically, if we define f of u to be 1/2 times 1 minus u squared raised to the negative a. Now again, the a I just wrote is not the same as the a in the definition in that theorem. The a in the theorem is a constant. The a here I'm using is that v over 2 minus 1 term. But if I define this function, I can then show that the function evaluated at 0 is equal to 1/2, which means I've satisfied that first condition. It's not equal to 0. It's neither equal to infinity nor negative infinity. then we get that u of 1 minus x of t is equal to 1/2 times this special sort of sum using this operator, n minus 1 times the function evaluated at 0 times that gamma I defined over n factorial, where again this gamma is simply this term here. Which is very pleasant, because now all I have to do is reverse the substitution. And if I remember, u is simply equal to the square root of t, which means I can square both sides. I can get 1 minus x of t is equal to this term squared. Rearranging, I get that x of t is equal to 1 minus this term. And if I remember, x of t is simply v over v plus t star squared, which enables me to write that t star is equal to, well, v over 1 minus, let's call it sigma squared, minus v all under the radical sign, where this sigma term, where sigma is merely 1/2 times the sum of this operator, special operator function, just like that. And that is essentially all there is, but I'm going to write it out very nicely real quick. So, writing this expression out, and I'm going to use the term k instead of the term n. I get that t eta sub v is equal to the square root of v over 1 minus sigma minus v, where sigma is equal to 1/2 times this sum 0 k minus 1. Make this nicer. Times this gamma term all over k factorial, where these operators evaluated at 0 polynomials in our A that we defined, and where ADA is simply 1/2 1 minus that confidence interval we're seeking, and V is degrees of freedom, equal to n minus 1, where n is merely the number of samples. So n is number of observations. We also need to note that, just for completion, that this evaluated at 0 is equal to 1, and that evaluated for higher terms, k terms, evaluated at some constant, say c, is equal to the derivative with respect to t of f of t times that operator on f with respect to t taken one value down or incremented down, evaluated at t equals that constant can be 0, where f of t in the above is simply 1/2 1 minus t squared minus a, and a is equal to v over 2 minus 1. And that represents the answer to a problem which, as far as I know, doesn't yet have an answer like this in this form. Thank you.